So, welcoming you to the offline class of structural analysis. Today, we are going to see about influence line for determinate structures. In that subdivision, we are going to deal about cantilever beam. So, IL for cantilever beam. So, for this purpose, consider a cantilever beam AB of length L. So, what is influence line diagram? It is the graph showing the variation of shear force, bending moment, reactions, displacement, rotations uh, with the variations while a unit load is moving from end A to B. So we are considering a unit load W equal to 1 kilonewton is moving from end A to B, and let us take this distance as A, because in most of the cases the cantilever is loaded from the free end portion. So this distance is taken as A. So now for obtaining IL, that is influence line for reaction A, that is RA. We know that summation of vertical forces is equal to 0, that is an equilibrium equation. So what are the vertical forces here? Minus W, that is acting in the downward direction, and we are having an RA and MA here, that is moment. Here we won't consider the horizontal reaction because the whole beam is subjected to vertical loading alone. So minus W plus RA is in upward direction equal to 0. Minus W in the sense RA equal to 1. So in the previous cases, while we derived the influence line for simply supported beam, we had the equations, general equations in terms of L and A. So we have applied the boundary conditions there. But here the RA value is 1, which is constant. So what will be the influence line diagram? The influence line diagram will be a beam over which there will be here also it will be 1, and here also it will be 1. So it is a rectangle of intensity 1, RA equal to 1. So this is the influence line for RA. So next step is to obtain influence line for MA. So moment about A. Taking moment about A, what are the forces we will consider? So this is A and this is L. So what will be this distance? L minus A. So 1 into, so it is in clockwise direction, 1 into L minus A. So the governing equation is MA equal to L minus A. So applying the boundary conditions here, when, what is the minimum value of A? It can be 0. 0 is possible. So A equal to 0, MA equal to L. Similarly, what is the maximum boundary condition possible? It can be 0, or the maximum it can be L. So A equal to L. MA equal to L minus L is equal to 0. So the boundary condition is, so it is moment about end A is, so that is this point, when A equal to 0 is L, and it is 0 here when A equal to L. So this will be, so it will be L, it will be 0. So this is the IL for, sorry, MA. force. So consider a cantilever beam. So we will find the influence line for shear force at a section. So consider a section. So let it be x. So the distance is, let it be small x. And we know that the length of the beam is L. So for considering this, we know we will consider two conditions, that is A is less than X. So that is when the load is in between this A and D region. So I'm considering the load to act here, that is W equal to 1. So now the distance is A. So now the A is less than X. So what will be the bending moment about X? We can take either this portion or this portion. So there is no loading in this portion. We can simply arrive that AMX is equal to 0. So then next moving on to the second condition, A is greater than X. Now we are placing the load here, W equal to 1 kilonewton. Now what will be the A? So this one will be the A. So now taking moment about X. So Mx is equal to 1 into, we are taking moment about this point. So it will be 1 into A minus X. So when, what is the minimum condition for A? We are taking for A to X. So the A greater than X. So it will be X and L. So when A is equal to X, Mx is equal to 0. When A equal to L, Mx is equal to L minus X. So what will be the diagram? So this is not for shear force, it is what we have taken bending moment. So we have taken bending moment. So we have drawn the influence line for bending moment. So what will be the bending moment here? So here it will be 0. For A to X it will be 0. From X it is 0 value again. And here it is L minus X. So what will be the value? L minus X. So we have obtained the IL for bending moment. IL for bending moment of a cantilever beam. Now moving on to influence line for shear force. Influence line for shear force. So what will take? A is less than X. So Fx is equal to taking shear force about X. So the loading is here. So we can take either left of the loading or right of the loading. So there is no load in this point when we consider this portion. So Fx is equal to 0. When A is greater than X, now A is here. We can take either this one or this value. So we know that Fx is equal to RA because RA is in upward motion. So plus RA. And we know that the value of RA is 1. So Fx is equal to 1. What will be the diagram for influence line of shear force B? So A is less than X, there won't be any value. And when A is greater than X, it will be 1 throughout. So here it is 1. So shear force, that is Fx is equal to 1. So this is IL for shear force. So now we have derived the influence line for reactions, bending moment and shear force. Let's see it in a single drawing. So consider a cantilever being A, B. So what will be the reaction ILD for MA? ILD for MA is a triangle. ILD for MA, that is L minus A, and it is L. So this is ILD for MA. So next one is a rectangle. So rectangle, so it is for ILD for RA, where RA equal to 1. So next one, so we are considering a section yet, and the shear force diagram will be, from that section there will be value, that is Fx equal to 1. So this is ILD. ILD for shear force at section, and when we consider bending moment, it will be governing equation is A minus H. This is ILD for bending moment at a section. So these are the values we have to remember, and these are the shapes which we should remember. So let's move on to the sum using influence line diagram. Draw the ILD for shear force and bending moment for a section draw the ILD for shear force and bending moment for a section at 5 meter from the left hand support of a SS beam, that is simply supported beam, 20-meter long. Hence, calculate the maximum bending moment and shear force at the section due to an uniformly rolling load of length 8 meter and intensity 10 kilonewton per meter run. So this is the problem statement given. So we have to find out the shear force and bending moment at a section 5 meter from the left hand support of a simply supported beam, which is 20-meter long, and we have to calculate the maximum bending moment and shear force at this section due to an uniformly rolling load of 8 meter and intensity 10 kN per meter run. So what is the statement given? It is a beam, simply supported beam. We have to find out the shear force and bending moment at a section 5 meter. So let it be D, point D. Let the ends be A and B. And the total length of the beam given is 20 meter. And it is subjected to an UDL of 8 meter span. Of 8 meter of intensity 10 kilonewton per meter, and it is 8 meter long. So first step is to find out the maximum bending moment. First step is maximum bending moment. So the condition is maximum bending moment at D due to UDL shorter than the span. So this is UDL shorter than the span occurs when the section divides the load in the same ratio. Section divides the load in the same ratio as it divides the span. As it divides the span. So what is the section here? It is D, 5 meter. How it divides the section? 5 meter by 20 meter. So this here let it be A1 B1. So this load also be to be divided in this same ratio, that is A1D divided by B1D. So which is equal to 0.25 meter. From this we can obtain A1D is equal to 2 meter and B1D equal to 6 meter. So the loading position is such that, so it is the beam A and B, and this is D, and it divides the ratio in the ratio 5 meter to 20 meter, and the loading is like this. This one is 2 meter and here it is 6 meter. So what will be the bending moment diagram? We will draw up to this section D, and we know that it is x into L minus x by L, which is equal to 3.75 meter. Here x is 5 meter. 5 into 20 minus 5 divided by 20 is equal to 3.75 meter. So finding out the ordinate for this one, so we have to find out the ordinate for the ends. So we have to find out the ordinate here and the ordinate here, and we have to find the area. So ordinate under A1, let the ends of UDL be A1 and B1. So ordinate A1 is equal to 3.75 divided by 5. So it is 3.75 at a distance of 5 meter. So 5 minus 2 is 3 meters. So what will be the ordinate here? 3.75 divided by 5 into 3. It is equal to 2.25 meter. Similarly, for finding the ordinate for B1, 3.75 by 5. So we have, as we are taking the ordinate at this distance, calculating the distance from this end, it is 15 meter. And we have to find out 15 minus 6. So 15 into 15 minus 6, that is 9 meter, equal to 2.25 meter. So this ordinate is 2.25. Here also the ordinate is 2.25. So now the maximum bending moment. So now the maximum bending moment is given as so what will be the maximum bending moment? Load intensity into area of the UDL, ILD under the load. So intensity into area of ILD under load. Intensity is 10 and area is 3.75 plus 2.25 into 8 divided by 2 is equal to 240 kilonewton meter. So second subdivision is to find out the maximum positive shear force. We have to find where we will obtain the maximum positive shear force. So maximum positive shear force occurs when we place the tail at the end of the section. We know this. So this is the point D. So 5 meter and this one is 15 meter. And we know that the shear force diagram will be like this. So this is negative and positive. So when the tail of the load is here, we will obtain the maximum positive shear force. So what will be the ordinate under B1? So ordinate at B1 equal to 0.75, that is here it is L minus H by L, that is 0.75, and A by L is 0.25. 0.75 divided by 15 into 15 minus 8. This is total distance and 8 is the length of the UDL. Is equal to 0.35. Maximum positive shear force is equal to intensity of load, that is 10 into area of the ILD under the load. So here it is given as 0.75 plus 0.35 into 8 divided by 2, which is equal to 44 kilonewton meter. So similarly, what is the condition for obtaining maximum negative shear force? So maximum negative shear force due to an UDL occurs when the head of the load is at D. So this is D. So it is only 5 meter. So it will be like this. So and we know that shear force diagram will be like this. And we know this values as 0.25 and 0.75. That is nothing by A by L. So this is negative shear force. So the maximum negative shear force is equal to intensity of load into area of ILD under the load is equal to 10 into, as it is a triangle, half into 0.25 into 5, intensity 0.25 and length is 5. So total is 6.25 kilonewton. So this unit is kilonewton. So maximum positive shear force is 44 kilonewton and maximum negative shear force is 6.25 kilonewton. Let's see some more problems in the regular class. Thank you.